Para pagarlo, lo dejo. De hecho, ya se ya. Ya inició. ¿Sí? Sí, ya está la cortinilla. Ya está la cortinilla. Listo. Hola, hola. Bueno, voy a empezar en español. Muchas gracias por venir todos aquí. Y bueno, tenemos el gran placer de tener aquí a Iván Deutsch. Iván Deutsch es un experto en óptica cuántica, información cuántica, teoría del control cuántico. Ha trabajado más de 30 años en esta área. Él es profesor de la Universidad de Nuevo México, es el encargado del Centro de Control Cuántico llamado CEQUIC. Es el fundador de una conferencia a la cual, bueno, yo y muchos de los que están aquí han ido muchas veces, que se llama SQUINT, on Western Quantum Information and Technology. So, Ivan, it's a great pleasure to have you here.
Muchas gracias, Pablo. Thank you, everybody. I very much appreciate the invitation to be here. Pablo, thank you for organizing. Thank you to the director, and thank you all for being here this late in the year. I know it's almost time for holidays, and so it's very exciting to see so many people here in the audience. So as Pablo probably mentioned, I'm the director of the Center for Quantum Information and Control, CQUIC, as we call it, at the University of New Mexico. This is our skyline in Albuquerque, New Mexico. Those are the Sandia Mountains. They do turn the color of Sandia, and they are also shaped like the slice of a Sandia. I'm also the founding director of the newly established Quantum New Mexico Institute, QNM. So you may see there'll be opportunities for fellowships to apply for, and I hope Pablo will share that information with you, because I think we'll have some good opportunities for everybody. And if there's one thing in my legacy that you may remember, this is our tagline: New Mexico is a quantum state. So, all right, very good. So let me get started. I'm going to tell you about neutral atom quantum computing. And maybe before I get started, let me just say, I very much encourage you to interrupt me with questions along the way and have this to be a conversation. So if there's anything, I have a lot of material, but it's sort of, will be, we'll see where we get, depending on what you want to discuss. Okay. So let me get started. So before we get started, here's an old slide that I stole from the internet. This is a slide that I think was made a decade ago about by Franco Nori, the race to build a quantum computer. And this talks about various platforms that were at that time considered to be leading candidates or maybe a little bit long shots. And they included superconducting circuits. This is the kind of platform that's being used at Google, at IBM, and others. Trapped atomic ions. These are systems that were, at that time, was the one startup company was IonQ. Quantinuum is now another company that's doing ion trap quantum computing. Silicon, quantum dots, well, maybe Intel's working on that. And then there are some kind of outliers, Microsoft's topological qubits or energy-sensitive diamonds. But you may notice there's something missing from there. There's no talk of neutral atom quantum computing there at all. And then I looked at this about a year ago. I gave a similar talk, and I looked for the same thing, the race to build a quantum computer. I found this slide. This is from 2024. And you notice there are the different platforms that are being considered, some ones that weren't considered before, photonic quantum computing. See, one of these things might be a laser pointer, I'm not sure, but in any event. But most importantly, you see the one that's kind of running ahead the race currently, which is neutral atom quantum computing. And it has come out of nowhere. Well, it really hasn't. It's been around for a while. Something we thought about in my group going back to 1999. And we wrote some papers thinking about doing quantum computing with, instead of atomic ions, atomic neutral species. And our motivation for this was that we could induce entangling interactions optically with induced dipole-dipole interactions. And let's see, let me go back. But importantly, what we were thinking about was that this would be a platform where we could have massive parallelism. We can, in principle, in parallel, do many, due to the sort of intrinsic way that we were going to manipulate these atoms that I'll tell you about, have massive parallelism, and this would be an retrievable, scalable system for fault-tolerant quantum computers. So we wrote this back in 2000, and here we are now in 2025. People are taking notice. So back in 2018, Science had a little article that a new dark horse candidate was coming onto the field for doing quantum arrays of atoms, underdog technology now in the race. And then in 2024, they think, oh, maybe this is the best way to do quantum computing after all. So it's really been an exciting and interesting time. And this has, gotten noticed. Now there are companies, startup companies that are starting up, thinking about making quantum computers where atom computing, inflection are some of the leading ones. And in addition, I'd say big tech is taking notice. So Google announced in 2024 that it's going to make a big investment in Queera. And the CEO of Microsoft got up and talked in 2024 about their collaboration with atom computing. So I think there are some new bets being made. Now, I don't have any stock in any of these companies. I'm not here to sell you on this from the point of view of companies, but I just think it's an interesting trajectory we've been on the last 25 years of how this new basic science has grown and the technology that it's coming out to here to tell you about it. Of course, all of this work in these companies, has its roots in basic academic labs. And there's been so many pioneers over the last 25 years or so in the ability to trap individual atoms in optical fields and manipulate them. And I'm not going to be able to do justice to tell you about all of them. But of course, so much of this, what's happening now and what's happening in the technology really has its roots in the basic science. All right, let's get started with the fundamentals. So why atoms? Why should we think about atoms as the right platform for doing quantum computing? And I would say fundamentally, it's because atoms are the basis of the most quantum coherent device in the world, and that is atomic clocks. Atomic clocks are incredibly well controlled, incredibly precise. Over decades of technological development have gone into laser cooling and coherent control. Basically, an atomic clock is a bunch of qubits. Each qubit is encoded in an atom, and the quantum coherence, the quantum oscillation of the two states of an atom, whether it be the two states separated by a microwave frequency in the current standard for a clock, the cesium atom is the standard of a second, and the precision with which we can know that frequency, the pendulum that is the ticker in our atomic clock, is, a part in 10 to the minus 15 or 16 in the current clocks. And it's now in other atoms based not on microwaves, but based on an optical transition in strontium, we're getting to precisions that are unheard of, where even the raising of the optical table by a few meters, we can see gravitational redshifts. So the precision with which we can control and measure quantum coherence in atoms is unparalleled. There is just no system in the world where we can do it, because atoms are perfect qubits. Every atom in the universe is the same. We don't have to calibrate the fabrication of what the qubit is. The universe gives us that qubit, and now with coherent oscillators, whether it be microwaves or the improvements in lasers, we have the ability. So the technology is there. So where's our quantum computer? What's the problem? See, in an atomic clock, what we have is a bunch of qubits, but by design, we try to keep those atoms from interacting with one another, from colliding with one another, from having any kind of interactions, because that ruins our frequency standard. We want the frequency standard of the atom in the universe, not the atom interacting with anything. And if the atoms don't talk to one another, we can't make the quantum logic that we need for a quantum computer. So the challenge then is to go from the ability to control single qubits in an ensemble of many to controlling the full many body state of a large collection of atoms, okay? And so there's a number of technological steps that have been important to get us to where we are today. And one of those steps is we need to be able to, if we're going to be able to do quantum logic and quantum computing on our qubits, we need to be able to address single qubits. We need to be able to talk to the individual atoms. And therefore, we need to hold on to them and trap them in a way that we can address them, and do it in a way that's very well controlled. So That's being done with so-called optical tweezers. An optical tweezer is just a focused laser beam. In this picture, you see here, the atoms are trapped in the focus of a laser beam. There's many of these in an optical array. We have many of these tweezers. The atoms are kind of randomly trapped in these traps, and then we can rearrange them. We can see where the atoms are and move the traps to make defect-free arrays in 1D, in 2D, and if you're in Paris, you have to make the Eiffel Tower and do it in 3D. So that was a real important development. How do you be able to trap individual atoms and arrange them in a way that you want that's going to be then basis for your quantum circuit, okay? The other part, as I said, is we need the ability to have the atoms talk to one another. We need to be able to have quantum logic, which involves controlling the state of one qubit conditional on the state of another. The entangling interactions are at the heart of a quantum computer. So atoms are great because they're neutral. And so you can get lots of atoms together without them talking to one another. But atoms are terrible because they're neutral, and therefore they don't talk to one another. But we can turn the interactions on and off by exciting the atoms to very high-lying orbitals. And those, when the atom's in the ground state, they don't see one another. But when the atom is in a very excited, so that's what's being shown here, it's in a highly excited orbital. The radius of the atom grows like the principal quantum number squared. And so if I'm in a high energy level, say I'm in n equals 50, then I have thousands of times, I can have the atom the size of, you know, a half a micron or so. And once the atom is that big and fluffy, it feels its neighbor, okay? And the van der Waals interactions between the atoms become very substantial. And that's essentially because they're polarizable. There is a dipole-dipole interaction between the atoms that we can turn on and off by exciting the atom to these high-lying orbitals and then de-exciting them when we're done, where they don't no longer interact with the environment strongly. And so the strength of this dipole-dipole interaction scales very rapidly with the principal quantum. N here is the principal quantum number. It's the number that tells me how excited I am. And in addition, when the atom is in these high-lying orbitals, it doesn't spontaneously decay. It lives for a very long time. The spontaneous decay or the decay from the excited state fundamentally limits. If I'm going to put the atom in an excited state, I have to do my logic well before the atom decays back down to the ground state. So the lifetime is important and it scales favorably. We'll have hundreds of microseconds, which is way longer than the time scale for doing the gates. Okay, so here is just to get a sense of how we can use this to do interactions. What's being shown here is the energy level diagram associated with two atoms, okay? So what's being shown here is, as a function of the distance between the atoms, this is the energy of two atoms. They're both in the ground state. If they're both in the ground state, they don't feel one another unless they're at about an angstrom apart, and I'm not even showing that here. If one of the atoms is in the Rydberg state and the other is in the ground state, again, they don't feel each other's presence except when they're like at an angstrom apart. But because of this sort of superatom, this blowing up this very highly polarizable atom, when they're both in the Rydberg state, so R, little r stands for Rydberg state, we have a strong dipole-dipole interaction, or van der Waals. That VDD is the van der Waals, and if I tune a laser beam to excite the atom from the ground state to the Rydberg state, I'm on resonance right here, but I'm off resonance for exciting both atoms into the Rydberg state. And so if that shift, that dipole-dipole shift is large enough, then I cannot excite both atoms to the Rydberg state. We call that the Rydberg blockade. So I can excite one atom, but not both. The second atom cannot be excited. It's blocked because that second transition is off resonance. And so that was the basis back all the way going back to 2000, after we had written our initial papers about this, a paper from Peter Zoller's group when Misha Lukin was, I think, a postdoc, based on doing this work. You know, what they were interested there, I don't think they fully appreciated what they were onto at the time. They were looking at our work and said, we want to make it faster. And so if we have a stronger dipole interaction by putting them in the Rydberg state, we can make the old proposal faster. But the Rydberg blockade was really the key point here. And you can see how this can lead to conditional logic, in the sense that I can have a control qubit, and whether I can flip the target qubit or not is conditioned on whether the first atom is in the ground state or the Rydberg state. So that gives me a kind of conditional logic, and that's the heart of it all, okay? All right, so let me tell you a little bit more then about the sort of the basis of how this works, okay? How are we going to encode a qubit in an atom, and how are we going to do the quantum logic associated with that? Okay, so as I mentioned, we're basing this on what we have developed for decades in atomic clocks. So the natural way to encode a qubit is the qubit we use for a clock. And that might be, these are called the clock states. So they could be the clock states in a cesium atom. The clock states in a cesium atom are in the ground electronic state. They are separated by 9.2 gigahertz, which are microwave. These are so-called hyperfine levels within the ground state of the atom. As I mentioned, the sort of more newer technologies for clocks are so-called optical clocks, and they're based on group 2 atoms. So cesium or rubidium is an alkali atom. Strontium is a alkaline earth. It has 2 electrons in the ground state. And because of that, there are these metastable excited states that are optically excited, and that's the basis. I could have an optical qubit. So both of these are both kinds of species. In fact, so in Quira, they're using rubidium. In atom computing, they're using strontium as an example. Right. Now, other ways that people have been thinking about this is encoding the qubit not in the electronic state of the atom, what orbital it's in, but in the nuclear spin. So the atom has a spin. The atom has a nucleus, and some of the isotopes have a nuclear spin. And so for ytterbium-171, which is another atom being considered for atomic clock, it has a spin 1/2 nucleus. So that's a very natural qubit. In fact, so there's another company starting up in Princeton where they're thinking about encoding the quantum information in the qubit associated with the spin 1/2 nucleus of a ytterbium-171 ion. And what I'll tell you about a little bit later about thinking about encoding not just in qubits, but maybe in a 10-level system, and thinking about a q-decimal. The spin of strontium has actually 10 magnetic sublevels, which could represent a register which has 10 different outputs rather than 2. Okay, and we can think about Schrödinger spin cat states. Okay, so let me tell you a little bit more about how does one do gates in this? What are the standard procedures by which one does gates in a to make entanglement in the neutral atoms. So as I mentioned, we can think about my two-atom system where I have, here are my two atoms. I have a ground state and this very highly excited Rydberg state, and I can excite it with a laser beam to this Rydberg state. If I think about this system where I shine the same laser beam on both atoms so that both atoms see the same intensity and the same frequency of the light, then I can rethink about this two-atom system, thinking about it as only the two atom states that are symmetric, right? So I have both atoms in the ground state, or both atoms in the excited state, or if I have only one atom in the ground and the other in the excited, I don't know which one it is. And so if it's symmetric under exchange, I have the symmetric state GR plus RE. Okay, that's the so-called bright state in the system. Now, the doubly excited Rydberg state is off resonant because of this dipole-dipole interaction. And so it's blockaded, okay? Moreover, there's another point I forgot to emphasize, which is that when I think about this in the two-atom basis, there is an enhancement to, so big omega here is the Rabi frequency. It represents the strength or the frequency with which I'm coupling from the ground state to the excited state. And if the Rabi frequency is omega sub light for one atom, it's the square root of 2 times that. That's called the super radiant effect, okay? But that's not so important. What's really important here is the following. If I have this Rydberg blockade, okay, and I get rid of the doubly excited Rydberg state, then if both atoms are in the ground state, I Rabi oscillate into an entangled state. I radiate from both atoms being in the ground state to this entangled state where I have one atom excited and one atom ground, but I don't know which one it is, okay? And that entanglement is coming from the Rydberg blockade. If that VDD were not there, it would be the separable system. It would be the system on the left. So the existence of the blockade and the getting rid of this is what gives me the Rydberg blockade. Okay, but it's kind of nice that it doesn't actually depend on what V is, as long as VDD is big enough. So it's sort of insensitive to where the atoms are, as long as this shift is big enough compared to the Rabi frequency, I get this entanglement, okay? All right, so this is going to be the heart of how we're going to make gates, okay? So the gate we're going to make is called the controlled Z. The controlled Z, or C sub Z, is a quantum logic gate which does the following. I have two qubits, and they can be either in 0 or 1, okay? If the this qubit I'm going to call the control, this qubit I'm going to call the target. If the control is in 0, I'm going to do the identity. I'm going to do nothing to the target. If the control is in 1, I'm going to apply the Pauli Z operator. That's why this is called the controlled Z. And as a matrix, what that does in the computational basis is it does the identity to the target or the Pauli Z to the target, depending upon whether I'm in this block or that block. That's called the controlled Z. And if I have the controlled Z gate, I'm making a relative phase between 0 and 1 in a way that depends on the control, okay? So I can explain that in more detail. I don't have a lot of details. I'm happy to answer any questions. So the controlled Z gate is an entangling gate. It can entangle atoms if they start in a superposition of 0 and 1, and I do this, if the control is in a superposition into 0 and 1, and I do this, then the two-atom system will be no longer separable. And this CZ gate is equivalent to the controlled knot. The controlled knot is a flip by local rotations, okay? So what we need to do this controlled Z gate is we need to have phases on the computational basis state. So this is both in 0, 0, 1, 1, 0, 1, 1. So if I look at a unitary map on my 2-qubit system that is diagonal, that just puts a phase if on 0, 0, a phase on 0, 1, a phase, oh, this should be 1, 0, excuse me, and a phase on 1, 1. That's a gate that is diagonal in the basis, okay? That gate is equivalent to the CZ gate if the following is true. If the phase of them being both in 1, 1 is not equal to twice the phase of 0, 1. If that difference is pi, then I can say that up to a local rotation on the qubits, this is equivalent to a CZ gate, okay? So the name of the game then is the following. Design an interaction which at the end of the day is putting a phase shift on the two atom states in this manner, okay? I want quantum control and quantum interactions is all about interference. It's all about phases. So if I can control the phase of the wave function, I have a tremendous amount of control. And I have to do it in a way that the phases depend on the interaction between the atoms. Otherwise, it's independent phases on each independent, and I don't have any entanglement. So these phases have to depend on the entangling interaction in some way. All right? Any questions? Please don't be shy. Yes.
Like you have the atoms in the array.
Yep.
And then I assume you shine light to another. So if I have a resolution to distinguish the atoms, do they become entangled?
So there are different gates that some of which depend on individual addressing and my ability to. So that paper from Yash et al. From 2000 required individuals, said, first I'm going to put the first atom in the Rydberg state, and then I'm going to do something different to that. And in principle, that would work. But in practice, it's not a very good, robust system because the laser beams are not that well controlled. And it's better to have a big, fat laser beam that looks symmetric. So in principle, I can do my gates symmetrically, or I can do them that are in a non-symmetric way that are local to the different interactions. The trade-offs for them are typically not theoretical, they're technical in the lab. So people like to do gates that are symmetric because they don't need that level of individual control. Of course, you also need individual control for, you can't do everything symmetrically. Otherwise, you're not accessing the full Hilbert space. So there's some combination of these things that are being used. Yes, please. Yeah, so single qubit gates are easy. They're called an atomic clock. But it depends. So an atomic clock, and this goes back to this previous question, in atomic clock, we're doing everything on the ensemble together. So we have a big microwave field that has a centimeter wavelength, and every atom sees the same thing. But if in a quantum computer, I need to do them separately. So I need to do this with something I can focus. So typically it's done with a 2-photon Raman transition, where the frequency difference between the two laser beams is a microwave. But then I have to control that Raman. Well, people know how to do that. Okay, so let me just then say, so there was a big breakthrough. So, let me go back and say, we made these proposals around 2000. What the heck? Why did it take 20x years before it worked? And the reason was really people didn't have the good enough lasers to do it. The lasers were not powerful enough and were too noisy. but also the protocols that were being used were not robust, right? This is what we were just talking about, the ability to not have to locally address, I can have a big laser beam and have things more favorable to the technical environment in the lab. And that happened, oh, I don't have the year. This is in 2023. This is called the Levine-Pitchler gate. So let me walk you through this to explain how this is done. And I'm going slowly. I'm happy to tell you, as many details. So again, so here is my atom now. This is my qubit. Remember, these are the clock states, say, in a rubidium or a cesium atom. They are separated by 9.2 gigahertz. This is a very highly excited Rydberg state, n equals 50 or 60. This is n equals 5, okay? And we're going to shine light on the system off resonantly. There's a so-called detuning. And it has a certain amplitude of the laser that represents the Rabi frequency and the phase of the laser, which we're calling Xi, all right? And we're doing it symmetrically. Both atoms see the same laser field, all right? Let's now look at the 4 different basis states, okay? So I have both atoms in 0. In that case, they're so far off resonance that is left alone. We have the case where one of the atoms is in 0 and the other atom's 1. We don't know which one. And that guy goes up to the excited state with one atom in the excited Rydberg state. Only the 1 state is coupled to R. 0 is not coupled to R, okay? But if both atoms are in the 1 state, then I have this Rydberg blockade. And the 1 state is coupled to this bright state, this entangled state, with a different Rabi frequency, with the square root of 2, okay? So remember what I want to do. What I want to do is I want to put a phase on these 4 different states in a way that depends on the entanglement. The entanglement is happening there, okay? All right, so what they did is they said, oh, what we're going to, each one of these systems is a 2-level system. This is a 2-level system. This is a 2-level system. I love gumming wrap on the board. This is fun. And each of these 2-level systems I can think about as rotations on the Bloch sphere. Okay, so in this 2-level system, I'm Rabi oscillating at Rabi frequency omega. At this guy, I'm oscillating at this Rabi frequency. And the phase of the laser determines the axis of rotation. So they had 2 pulses where in one case, if I was here, I would rotate by this amount, change the axis, and then rotate back over here. Where this guy rotates faster, goes around a full 2 pi, and then another 2 pi. Okay? At the end of the day, after these pulses, the atom's back in the ground state. It's in either 0 or 1. But because of the trajectory that it undertook on the sphere, it subtends a different solid angle because of the different Rabi frequencies. And the phase that's accumulated by the wave function depends on that solid angle. So they were very clever and chose us in such a way that the difference in the phase between these 2 things was exactly pi. And they made the CZ gate. And they did the experiment, and they got pretty good fidelity. The fidelity F there is the yield. That's to say, how good is my gate for all of the 4 different input states averaged over them. And it's over 99%. This was a breakthrough. No, the highest up to this point was 80%. No one had gotten anything this high, and it changed the game. Okay, this was a paper out of Misha Lukin's group in 2023, Misha Lukin from Harvard. There have been Other demonstrations more recently where they're getting higher fidelities by just tweaking this and doing it a little bit more optimally. Okay, so what is the state of the art currently? There's been a lot of developments which has made this exciting now. One of them is just the whole architecture. So what's being shown here is a movie of atoms being moved around through spatial light modulators that move the focus of the laser beam and thus move where the atoms are. And boom, shine on a laser beam, boom, shine, and you see those little red circles all in parallel. Remember we said from the beginning, the parallel architecture, all can be done at the same time. We can do parallel gates in a system. Moreover, there is this sort of zoned architecture whereby we can have different zones where we store atoms, move them in to do entangling gates, and read them out. So the ability to do gates and integrate the architecture in a way, and what's I think also very interesting and important for the atomic system is there aren't any wires. It's not like in a superconducting circuit where I need a cable that comes in that brings microwaves to the transmon that I have to get into a Dewar. This is all at room temperature. It's just a spatial light modulator. It's optics. It's optics. Optical engineering is the whole story. It's just done with light. It's not with smoke and mirrors. And and these things are scalable to the degree to which we have laser power. So in this incredible experiment that was recently published in Nature from Manuel Endres's group, they have over 6,000 qubits now, very high quality qubits. They've done an incredible, careful job of seeing the degree to which these things are really well controlled. And we're moving now into a era where people are trying to build now so-called logical qubits, qubits that are encoded in many physical copies in a way that people can do quantum error correction. This is why people are really excited about the system as a potential scalable platform. All right, so let me just tell you maybe in the last, 10, 15 minutes, I want to make sure I leave enough time for questions. Maybe before I go on, I'll pause for any more questions of anything that I discussed. Yes, please.
Level atom.
Yes.
So, and you just mentioned that the Rydberg states are very stable, okay? So, but what happens to the transitions that are not to the ground state but to the other side in between?
So when the Rydberg atom decays, it actually dominantly doesn't decay back to the ground state. It dominantly decays to a nearby other Rydberg state because there is stimulated emission due to just black body that is, at gigahertz frequencies. So there is a kind of cascade down. So it's actually something that's discussing with Pablo. We've isolated 3 levels in the atom. The atom has an infinite number of levels, and there are many in between. And when the atom decays, it actually decays into other levels in a way that we can find it. So that is what we call leakage. It leaks out of the computational Hilbert space into other energy levels. Leakage is a catastrophic error to a quantum computer if we don't detect it. But if it goes into another level that we can shine a laser field on with an allowed transition and have the atom fluoresce, then we can know that it actually leaked. And then we can erase the qubit. And that actually is extremely powerful. So there's new ideas that are developing along the way, things that people knew about 25 years ago, but now when people are trying to actually build the systems, they're seeing what are the dominant errors and they're integrating them into the kind of codes and error correcting strategies that are being used. You had a question as well? Yeah.
When I put the tweeter, my atom card vibrates.
Yes.
How much of that affects it?
It does. It does. A lot. It affects it in two major ways, or maybe three. One is there is a Doppler shift. So the frequency that the atom sees depends on its velocity. So this detuning delta depends on the velocity. In addition, if the laser beam is not homogeneous in its profile, the atom moves, it sees a different intensity. That affects omega. In addition, I said that the van der Waals interaction is a very strong function. Now, the blockade kind of helps us with that. So there's a lot of effort that's done to laser cool the atoms to near the ground state. But it would be nicer if we had gates that were more robust to that. But it is an issue. Yeah.
It's in the same direction. This is a technical limitation, which is a challenge.
Yeah.
So which are the biggest challenges for scalability to make many devices?
For the neutral case or for any? Yeah. I mean, so there are a number of issues. One issue is the atoms are not very strongly trapped. Unlike in an ion trap, where they have electrostatic charge and you have very strong forces and you can hold on to them very strongly, they're not in a perfect vacuum and there are air molecules and they can knock them. So the atoms have a finite lifetime in the trap, and because it's a very shallow trap. In addition, you're moving the atoms around, right? And when you move them around, you might lose it, you might heat it up, okay? And so atom loss and atom heating is a challenge, and people are thinking, and we worked on a problem associated with that as well. How are you going? But you see, unlike in a chip, if I have a cosmic ray and it comes in, and it's actually a problem, into a transmon, you're screwed. Excuse my language. You know, it's there. Whereas the atom, you have a reservoir, you can bring in a fresh atom with a new tweezer if you can know that the atom's lost and you can cleverly detect that, then you can replenish it, okay? And so there's all kinds of, so that's one issue. Atom loss is a big issue, and heating. There's just a general speed issue, which is, you know, your move, oops. I don't know why it's not wanting to do this, try again. You know, how fast can you move the atoms? You can't move them that fast, otherwise you're gonna, so, you know, people worry about that, but I personally don't think that's a big issue. Because in my view, a quantum computer will never beat a supercomputer, classical supercomputer, unless the problem is exponentially harder. And once it's exponentially harder, it's either never or a week. I'll wait a week for the answer. Maybe I could have waited a day if I had a faster clock speed, but if it's a week versus never, I'll take a week. So I think that the clock speed is a red herring in my view about these things. If it works perfectly, I don't care how slow it is. If it's the exponent will win. The other issues that are really critical are just about lasers themselves. Now, I'm not an experimentalist. I just play one on TV. I'm really a theorist. You know, I work closely with the experimentalists, and the issues really are about, you know, the lasers we work with are UV lasers, and to make UV photons, we have to, you know, so the laser issues are all kinds of issues of phase stability and intensity stability and all of that. And then there's power. You know, these 6,000 qubits are done in one giant laser beam that is split up into these 6,000 foci. So you need a ton of power to split up into all these spots. And then you start heating things up and, you know, so there's, you know, so there's engineering issues. But I don't think they're that fundamental. Yeah. All right, maybe I'll continue a little bit more. Okay, so let me tell you a little bit about some other things that we are personally working on. So I mentioned this point earlier about going beyond two-level systems. So I want to ask everyone a question. Why should we quantum compute base 2 with qubits? Well, maybe a different question. Why do we classically compute base 2 and not base 3 or anything else? Why do we do that?
Flow of energy, flow of current.
Yeah, we do that, but because in some sense, practically speaking, it's easiest, I would say, to read out yes or no. If I have to read out yes, no, or maybe it's more complicated. And so, I mean, it's actually most efficient. I read something, I don't quite understand. If we could encode in natural log base E, it would actually be the best. And so a trit would actually be better, but for classical, but we don't do it for practical reasons. I think it's a similar reason in quantum computing, in that we want to read out and manipulate. It's sort of easier. But I think in quantum computing, the story is more complicated, because a quantum computer, in my view, what makes a quantum computer powerful is that it is both, in some sense, analog and digital at the same time. It's analog in the sense that I can go continuously between the 0 and 1 state on the Bloch sphere. But if I did that and I couldn't digitize errors, I would be screwed, because errors would accumulate in a way that would make it not useful. The ability to do error corrections, because I can digitize those errors and therefore get rid of entropy. Otherwise, I would never be able to make a quantum computer powerful. So, but where is that digital versus, it's a different space in quantum, in my view. And the question of where the fault tolerant thresholds are going to be better, whether it's going to be for qubits or beyond qubits, it's not a solved problem. So we've been thinking a little bit about encoding in what are called qubits with a D, which means D level systems bigger than 2. And this could be interesting. We could have a bigger Hilbert space. It's only a logarithmic improvement, but nonetheless, if you have, you know, still a factor of 3 or something like that, and maybe in terms of the way in which you make your quantum circuit, how you trade off entanglement versus internal control can be different with different level systems. And you might encode a qubit in a QDIP. So there's various things, but you need to do your logic. You need to do your quantum logic now differently than you did with two-level systems, because instead of just rotations on the Bloch sphere, which is the group SU2, you need to do SUD. So that's complicated. So let me just, in maybe some few minutes, tell you about that. So I'm going to tell you, remember I told you about the strontium atom. The strontium atom has a spin of its nucleus. Its spin is 9/2. And so the number of different sublevels in the spin, the magnetic sublevels, is 10. We call this qdecibel, okay? And there they are. There are my 10 levels. And we can control that spin with a magnetic field. That magnetic field will cause the spin to rotate. But that rotation is not the full set of quantum operations. That is actually a 10-dimensional representation of SU2. That's just Larmor precession. That's really SU2. It's a representation of SU. It's not SU10. I can't make any arbitrary superposition with just a big rotation like that. So I need something more. And we can do that because we have light around. And the light allows us to manipulate the spin in ways I can tell you about with questions. Okay, but I want to just tell you the essence here. Okay, so this is work done with my colleague Mike Martin at Los Alamos and some of my students who are now gone on to bigger and better things. Shiva is now actually works for JP Morgan Chase, the bank. He works on quantum error correction because they're trying to make quantum algorithms to make money. God knows. Anupam is a postdoc at Lawrence Berkeley National Labs. So here's the idea. I have my magnetic interaction. My magnetic interaction, for those of you who know, this is the interaction between the spin of the nucleus and the magnetic field. Okay? But in addition, I'm going to shine light on the atom. Shine light in a way that is far enough for presence that the atom doesn't spontaneously emit, but it causes a shift in a level that is not linear. It's quadratic in the spin. This is what's called the tensor light shift, and it's a well-known effect in atomic physics. Okay, so the point then is the following. I can manipulate the spin. The spin is called I. That's an atomic physics notation. It's a spin of a nucleus is called I instead of J or L or something like that. And so I have a magnetic field that's in the transverse plane that I'm going to rotate with some angle phi as a function of time. That's my magnetic interaction. That would just cause linear interaction. But then I have this nonlinear light shift, which is quadratic. Okay? So the name of the game here is to be, say, there's physics. The physics tells me how I can talk to the spin. I can talk to it through magnetic fields. Through magnetic fields, I have these things that are linear in the spin components. I can talk to it through the light. That gives me this nonlinear. And the question is, can I put this together to make an arbitrary evolution on my 10-dimensional system? And the answer is yes. And the answer is yes through this theory of group theory. The fact is that I can, by putting on pulses that alternate these different interactions, I can cause the system to evolve in any way. And all I need to know is what is the time-dependent angle as a function of time. That is the problem which we call quantum control. Quantum control says, is the system controllable? Is there a way, in principle, to get to an arbitrary, unitary evolution in the system? And the answer is yes, if I have the right generating set. And then the goal is to find that map. And how do you find it? We find it numerically. We integrate the Schrodinger equation until we find the best solution. And there's a whole theory of quantum optimal control of how you optimize the wave function efficiently to find that. And just to give you a picture here, here's an example. And this will be kind of, I think, my last story. So what's being shown is the following. Suppose I want to make some weird superposition. This is a superposition of I equals 9/2, m equals 7/2 with I equals 9/2, m equals -7/2. This is a picture of the density matrix. The diagonal is the population. The off diagonal is the coherence. So this is my target. I want to make that state. This is my initial condition. My initial condition is that I've optically pumped all the population into the stretch state. I can do that with atomic physics. I can put it all there. And I want to get from here to here. And I say, computer, find the wave function, or the wave form, that's to say the phase of the magnetic field oscillation as a function of time, as a pulse sequence that gets me, and it finds this. And here's a movie of what happens as a function of time. So that's the wave function. What's being shown on the bottom is the so-called spin-Wigner function. The spin-Wigner function is a kind of quasi-probability distribution on the sphere. Ta-da! So what's the point of this movie? The point of this movie is to say, this is incredibly non-intuitive. I mean, you would never say this is how you get from there to there. I mean, the wave function is doing all kinds of stuff. The density matrix is doing all kinds of stuff. And then boom, it gets to the right answer. Okay, that's a very good question. There's something known as the quantum speed limit. So given a certain amount of power in the system, there's only so fast I can get from one step to the other. And so what we do is we start with a time that we know is long, and we keep pushing till we hit the speed limit. And then if we go shorter, we see we can't get anywhere. The solution is not unique. So there are many, depending on our initial seed, we can get many different solutions, and we find the one that is most robust also to decoherence. But this is a very powerful tool that we are now employing to be able to do arbitrary interactions. And I'll just say, we can do this for gates too. So for gates, what I want to do is I want all 10 basis states to go simultaneously to their final. So what I showed you there was one state going to some final state. Now I need all 10 states going to 10 orthogonal states, and we can do that with one waveform that simultaneously does the right thing on all of that, and that's the way we can design an arbitrary SU10 gate. It's different than thinking about SU2, where we say, oh, I just want to Rabi oscillate. Here, I'm using the time-dependent interactions to modulate the system in such a way to generate what we want. All right, I will conclude there, I think, and just leave you with some references and take any more questions. Thanks for your attention. Yes.
More questions?
Thank you for this very nice talk. Is there a rule of thumb to determine whether a system is controllable or not?
Yes, there is a theorem. So, right. So I didn't discuss this in detail, but I said these words here, Lie algebraic generating set. So if I think about if my system lives in a finite dimensional Hilbert space, then I can say that I want to generate the evolution in a particular group. The Lie group in this case is SU10 or SUD, where D is the dimension of the Hilbert space. Let's say, what does it mean to be the generating set? What it means is that, so let's think about SU2. SU2 is generated by rotations around an arbitrary axis. But if I want to make a rotation around an arbitrary axis, I really only need to rotate around two axes. If I do a rotation around X, and then a rotation around Y, and then a rotation around X again, I can actually generate a rotation around Z, because rotations around X and Y don't commute. So that's called the Euler angle decomposition of a SU2. So the X and Y rotations are a generating set for the whole group. So what I have to check is whether the set of Hamiltonians that I have, which is this, and this form a generating set for the whole group. And the way I test that is do multiple commutators of those operators span the algebra. That is to say, they have to be a linearly independent set of matrices. So it's based on the theory of Lie groups. Yeah. Or whatever you need to be able to modulate. So then we have to ask the question is, what are the restrictions on these functions of time? And so there are practical considerations. So the question is, do I have infinite bandwidth? Can I control it very fast? Or what if I'm constrained in some way? So there are practical considerations on the experiment. Like, for example, here I showed these sharp jumps in the phase. In practice, there will be some slew rate, there would be some bandwidth. So one has to combine the pure theory, infinite bandwidth, perfect to the practical in these things. Yeah. Yes.
So that slide regarding Pablo's last
question,
sorry. How do you measure the quantum speed limit, or how do you characterize it with your experiment?
Right. So, I mean, numerically, so the quantum speed limit is something that we cannot analytically derive when we have a time-dependent Hamiltonian. So the way we do it is we numerically, so here you see there are two kind of parameters. The way I've parameterized this phase is by the total time and by the time of each pulse, okay? So we have some number of little pulses. The number of pulses we have depends on the number of parameters we need to define the state. So we have delta t fixed, but then we can change. So we take the total time and we chop it up into n pieces. And then we numerically just compress it until when we go faster than that, we find. And what you'll see is that the infidelity goes like this. And, there's a cliff. It's very clear to see where that speed limit is. If you're very close to the speed limit, you're much more highly constrained, and it's much harder to find the optimal path because the fidelity is a function of all the parameters that we're putting in here is a vector of these values. So the fidelity is a function of it's like a metasurface. It's a function of a vector. And the question is, can we just use gradient descent to climb to the peak? Or is the nature of the optimization space such that we're going to get trapped in a local minimum? And that's been long studied for these optimal. What is the nature of the control landscape? Is it easy to find it's typically optimization problems are very hard. And we're going to get trapped in a multidimensional optimization spaces. But it turns out, for very lucky reasons, this problem is favorable. And it doesn't have saddle points or local minima that we're going to get trapped in if we have enough time. Of course, if we take too much time, we have decoherence. So there's a trade-off between doing things as fast as you can to have the coherence time be good and being robust to your control. Yes.
Is this great problem?
Yes.
For us to like an error?
Yeah, that's always a good question. The answer is yes. So there's two aspects of this landscape. One is, does it have local minima? And the other is, what is the curvature? So if your maximum value is a very sharp spike, then if you're off by a little bit, you're gone. So the Hessian, the curvature of this surface, again, is very favorable. It's long been studied. And in fact, it's fairly forgiving. So although it looked like, at the end of this movie, it just like went off. What happened if these pulses were off a little bit? How far off would I be from the final solution? And the answer is, it's a pretty favorable thing. Yeah. Yeah. I don't know when I'm happy to go as long as, yeah.
So in the Google Mass,
Yes.
It's not, I don't know if it's a convex optimization. I guess it's not convex. So when you do that, then there is a problem, because you never know if you get to the right point. You might get to a point, but there is not the right point. And you talk about local minima, but how do you know that the point you get at the end is exactly what you want?
Right.
And the other thing is, you talk about these proofs. No, there are proofs of
the Hessian and so forth. Yeah.
So, is this proof constructed so that you know quality proof and then use numeric part on this proof, or how do you do the numerics? How do you know how to get to this?
Right. So the optimization that we're using here is actually not convex optimization. This is just a gradient descent. So we have a cost function, or equivalently an objective function, whether I put a minus sign. And this particular algorithm, which is called the GRAPE algorithm, is a way that allows us to calculate the gradient of our objective function efficiently. So we calculate at every local point in time what the gradient is of our objective, and we just keep going up there until it stops, until the gradient gets close to zero at that point. Or we say that our objective is below 10 to the minus 4 or something like that. So numerically, we're just stopping when we get to a point that we're satisfied with. Okay. The proofs are based on looking at the analytics of what this objective function is and the nature of the landscape. That's to say, whether it is a convex function or not, or whether it has local minima or not, whether it has saddle points or not. What is the measure? Is it a set of measures 0 or a large measure where I'm going to fall in them? And so the work that I'm most familiar with is really a matter of just looking at what the landscape is and its favorability to gradient descent. That's what I'm familiar with. But operationally, we numerically just stop when we're good enough.
That is not local.
We don't, but we're happy if we get a fidelity of 10 to the minus 4. So something better, who cares? That's our attitude. Yeah. Yeah.
But I have tomorrow, just Friday, we are going to tomorrow morning, and Friday, we'll be back. Any student after the IIMAS?
Yes, I would be very happy to talk to you.
Thank you, Professor. Thanks a lot for the
Yeah, that was great fun. I enjoyed it.
I really hope to see you tomorrow.
Please come.
Yes.
Yeah.
Thank you very much.